Welcome to Core Concept 12. We will speak about gravity or gravitation as the curriculum seems to be calling it, or the A-level curriculum calls it. And I think they don't have it on AS level and they only have it for the A-levels, but nonetheless, I think this is a rather fundamental part of physics that one needs to know, and we'll try and talk about how they seem to want to test you for it. Right, so let's begin with. We're not going to get into the science of gravity and special theory of relativity and all of that. Gravity is a subject on which I think people are still trying to figure out where the equations will converge. But we will just look at it purely from the Earth's gravitational field and the perspective of the forces that it generates. Right. So we begin with what is called as Newton's law of gravitation, right? What does it say? It says the force between two objects, I'm going to write it down, the force between two objects is directly proportional, right? And some of the things you got to remember to the product of the masses of the two objects. So you've got mass of one object, m1, right? And the mass of the second object, m2, right? And inversely proportional to the square of the distance between their center of masses. And that's one of the reasons I wanted to do this after I speak about center of masses. And maybe the curriculum has it in A level because they talk about center of masses of three-dimensional objects and uniform bodies such as spheres. So maybe that's why they put it after that. But I think nonetheless, it is the distance between the center of masses of the two objects being spoken about, right? That's what it is. I want to illustrate that just to drive the point home. So I have here, let's say, the Earth, and I have here, let's say, the Moon. Though the scale, they're not similar in scale, but right. But I want to state that this is the radius of the Earth, r, right, and this is the radius of the Moon, small r. Mass of the Earth, uppercase M. Mass of the Moon, lowercase m. The distance that is being referred to here is the distance from this point to this point, right? And we have to be very, very clear because that is where problems can confuse you. This is the distance. The distance is not from the surface, right? So they can set up some problems where it appears a little interesting, where they unnecessarily give you d greater than equal to r and all that. I don't know whether they attempt to be overly accurate in their English or what the reason is, but understand the fundamental concept, right? So in this particular case, I should write not there. I should write it as m1, and this is m2. So m2, and that's what you would get. Now, as we always do, we love to re-engineer our world to create constants. But in the case of the Earth and other large celestial objects, experimental data is pretty solid, and we can write the force of gravity as equal to a gravitational constant times mass of the Earth, usually, because this is with another object, but I'll just write it as a generic notation, times the square of the distance. This is called the universal gravitational constant, UGC. That was nice, but that's the typical term. This relationship is Newton's law of gravitation, and you know how to state it. It states that gravitational force due to gravity. Some people write it as F with a subscript of G. is directly proportional product of masses, and the inversely proportional to the square of the distance between the center of masses. Right? Be very, very clear. Center of masses. Center of masses. Do not forget that. Okay, now, what do we need to know? I mean, problems can give you this, but let's try and understand what happened. I mean, we've seen cases where, I've dropped something. What am I going to do? I mean, I don't have the universal gravitational constant and all of that. But what I do know, that if I was on the surface of the Earth, somewhere, and I had a particle of mass m sitting on it, mass small m, sitting on it, right? I know that it's experiencing a force mg, right? And that force mg is experienced towards the center of the Earth. It's experiencing mg, I know that. I also know that that's the radius of the Earth. So that whole thing in the white line is the radius of the Earth. And that's what I'm experiencing. I can now try and build this relationship that says, well, we know our large gravitational constant, we know that part, but my simple small mass m is experiencing mg, right? But since we never want to believe that Newton can be wrong in his law of gravitation, he isn't, this holds, it would be equal to saying mg is equal to g times my little m times a huge m, sometimes written as me for the m of the Earth, times, what's the d squared now? D squared is nothing but r squared now. Radius of the Earth, so sometimes written as r with a little e there, sometimes m with a little e, but that's effectively what you get. And if I take out my m on either side, the small m, which is the mass of my own object, I can safely write this equation in terms of that big G as equal to, G is acceleration due to gravity times the radius of the Earth squared divided by the mass of the Earth. This is pretty much where they try to keep all their problems on the paper, so try to give you all these interesting problems. But anyway, let's just say your exam question might tell you that, if Newton's law says this product of this divided by distance, and given an object placed at a distance x above the surface, and it's usually a nominal distance, right, such that x is greater than or equal to r, prove that g is equal to gr squared by m. This is like an exam question for like 2 marks or 3 marks, and it's basically just this. So you equate the two, and you can arrive at this distance. And often you'll get r, most r's, if they give you a distance which is just minuscule compared to the massive size of the Earth, it's effectively, you can write the assumption that I'm treating it as being on the surface of the Earth, and that's the relationship where m, uppercase m and uppercase r are both related to the Earth, and you get the value of the gravitational constant. Acceleration due to gravity is also a function of the Earth, so that's why the gravitational constant is defined as being sort of a constant. It doesn't really change, right? Universal gravitational constant, as they call it. So that's where most problems seem to be in gravity. They don't seem to go, they try to increase the complication a little bit when they talk about rockets that are farther out. That's a little bit different, right? You fire a rocket up, and it has its distance is fairly, it's gone out of the atmosphere a little bit. They try to equate it with energy. That's a nice one, right? You have potential energy, and that potential energy is basically, defined at this point on the surface of the Earth. And then when you're farther away from the Earth, you have the force there, gravitational force, that's pulling it. And then they ask you, what is the work done by that force? that work done by that force is effectively the conversion of the kinetic energy to final kinetic energy. As you bring it down and its velocity increases, you could term that as the work done by the gravitational force. So there are some interesting variations that they throw at you, but this is fundamentally the part of or the equations that you need to know and understand, and most importantly, know that the distance is from the center of the Earth for almost all problems that they position to you. So even if it's for the rocket and they give you a distance from the surface of the Earth, you have to add r to that, where r is the radius of the Earth, in order to establish this equation, right? Otherwise, you would not get the right answer. Most of the times, give you the values for all of these assumptions, and if they do, then it's quite easy to calculate this. They almost always tell you to give you a value of g, and usually never ask you to get a value. Yeah, I think it's like 6.6 times 10 to the negative 11 or some ridiculously low number. Again, imagine, because the mass of the Earth is so large. But if they did set you up on something like that, then they wouldn't ask you for the last decimal place. It would probably just be 2 or 3 significant figures they would be interested in. But I think this should address it. You can understand that if you're breaking free from gravity, or if you're moving against gravity, such as a rocket does, you're still experiencing this force, but you need to generate more. Your acceleration is to be greater than to go past this force. So that's another way they can position you a problem. All you have to do is identify that in order to accelerate at a certain speed, I have to be break past this force, right? And then you can, if you don't have that value, you remember this formula and substitute in. You effectively will solve it. So yeah, I think this is it. So very, very simple, hopefully easy to take a look at gravity. Again, shows up in A levels, but every now and then there's a nice and easy, simple question that is unnecessarily complicated, as always, because they want to test your mathematics. But good luck with that. And I think I should have all of my core videos also done, and we'll see whether we discuss problems and other parts of the curriculum. But otherwise, all the best.